Hello and welcome to another Coffee with Developers. I'm here with Stephen Jones from Nvidia, and we're going to talk about solving all the computing problems that we have in the world right now. My problem is, and a lot of problems of you out there as well, is that you're actually having a lot of machine power in your laptops and your desktops and your mobile phone. And most of the time, the applications that you write in certain languages cannot actually take advantage of all that functionality. So as a JavaScript developer, I got one thread and I have no access to the different cores. So one of the products that actually try to fix that kind of gap and try to help you to actually get the best out of your hardware performance is CUDA. And it's an Nvidia project. And Stephen is one of the main architects or the chief architect, but we talked earlier that it doesn't make much sense to be a chief of if there's only one person to chief architect it. But anyways, so Stephen, why don't you introduce yourself and how did you end up in that role?
Yeah, hi. So I am Stephen Jones. I've been working in CUDA since 2008. I joined CUDA after quitting my PhD. I decided I didn't want to be an academic, and I joined CUDA when there was about a dozen people in CUDA. So I wasn't one of the founders of CUDA, so to speak. That was a guy called Ian Buck. It derived from his PhD project. But yeah, so I joined in 2008, and there's no real title of architect. You just kind of become that if that's what you're interested in doing. And NVIDIA is very good about that, actually. NVIDIA lets you sort of pick a thing that needs doing and act to do it. And the thing that was needed was more sort of herding cats and making different things happen across CUDA. So we grew it from 2007, I think it came out. 2008 when I joined, and I've been working with it ever since. I spent a brief period at SpaceX for a few years where I went from being a CUDA creator to a CUDA user, and that's always really interesting because when you build something, you build all these things, and I don't have time to sit down and really use them in a real project, right? I write algorithms. I think my first job at NVIDIA was writing the FFT libraries for CUDA, but when you design all these things, you make a lot of assumptions, and then you go and become a user, and suddenly all those assumptions hit you in the face again, right? And you realize that maybe half of them are right, half of them are wrong, and then you realize you're no better than a toss of a coin, and that makes you pretty humble about the things that you do. But yeah, it was an interesting transition going from making it to using it, and then after SpaceX, I went back to NVIDIA and continued on making more CUDA. And it's actually, I recommend anyone who's an engineer to go and actually use the thing that you build, because it's a very different experience from the other side, from all the things, all the work that you do, and all the decisions you make. So yeah.
Yeah, as a front-end person, I always found it the same way. Like you're in user testing, you're behind a two-way mirror, and you feel like a cop actually looking at what people are doing, and you see them getting stuck at the most obvious things to you because you're too close to the subject matter. You know how the thing works, so you know how to use it. But people come up with demands that you have no idea of. Which brings me to the main question right now, what is CUDA? Is it a framework? Is it a language? Is it what? Why should I, as you said, every engineer should take a look at it. What is it?
It's a big and complicated, it's a platform. It's a big thing. And it's grown over almost 20 years now. And so where it started as effectively a language for controlling low-level graphics chip hardware, it's evolved into a platform of compilers and libraries and SDKs and frameworks and still multiple languages now. You can do C++, Fortran, OpenCL. We're working very hard very soon. We're going to be Python, a first-class piece of CUDA as well. And so, it's basically anything that gets you access to the GPU goes through CUDA. There's layers of drivers and languages and libraries which are GPU accelerated. So if you take a program and you either call someone else's function that uses the GPU or you write something yourself, you're using CUDA. So CUDA is much bigger than just the language. People often think the language, and I started out working on the language as the architect of the language, but now I spend my time looking up and down the whole stack. And one of the key pieces about a platform is that all the pieces work together, right? So all the stuff that we put into PyTorch we actively upstream a lot of GPU accelerated code into PyTorch. You can embed CUDA kernels of your own. You could write something in CUDA Fortran and inject it into PyTorch if you were crazy for some reason. I don't think anyone's done that, but you could do that because everything in the stack agrees with what a memory handle is and what an executable kernel is and those types of things. So it's this interoperation that makes this whole thing a platform. And so basically, in my maximalist view, if you like, is that anything that gets you touching the GPU, you're going through CUDA in some way or other, whether it's low-level assembly language, high-level frameworks, even other people's languages. A lot of people have built languages on top of CUDA. And in some way, that's our superpower, is that the more people grow it and build their own things and specialize it in their own ways, then the more people get access. We can't write more than a couple of million lines of code, but there's literally millions of developers who've built tens of millions of lines of code on top of it. So it's this whole, it's an ecosystem, it's a platform of GPU access at this point.
I got stuck at at one thing that you said, which was Fortran. Fortran on GPUs? Fortran on multi-core? Who uses that?
So the original genesis of CUDA was to do parallel programming, and the first customers that we approached were really big supercomputing people doing physics simulation, people doing biology simulation, chemistry simulation. And so a lot of the physics in the world is still written in Fortran, just like a lot of the databases are still in COBOL. And actually, that's unfair to the Fortran guys. They're gonna hate me for that. But yeah, there's a huge amount of Fortran code out there, and most of your weather forecast is still done in Fortran. And so if you want to be reach the users and be able to accelerate the code that people already have, then you need Fortran and you need C in the supercomputing world. That's actually interesting because it's shifted enormously now. AI has exploded. GPU acceleration is, of course, a huge piece in AI because it needs enormous computation. And while the problems are actually very similar, scaling a giant weather forecast or scaling a giant AI training looks very similar in the technical element. The language of AI is Python, where the language of simulation and physics is C or Fortran. And so, I've been a C++ programmer for 30 years. And so all my intuitions are C++, but the AI world is all Python. And so there's this interesting gap that from my perspective, I have to bridge. I've got brilliant people around me who are amazing Python programmers. From the system software layer, it all looks the same, but the nature of the people using our stuff, the needs of the Python programmer are different from the needs of the Fortran or the C programmer. And so this new space is a learning curve for me as much as it is for any of the other people coming onto it.
As somebody who defined a language like the CUDA language in itself, when you just said like Python is the AI language, I feel for the people that do F# and R, because they were meant to be like the machine learning languages and the optimized ones for that use case, but everybody jumped onto Python. Is it because it's easier, or is it because they already came from other use cases and went to it?
I mean, in my opinion, and I've obviously written Python, but my day-to-day is in C++. But the productivity, the ease of use, and in many respects, I think just the scale of the Python ecosystem makes Python a really good target for whatever you want to build. And I've done 3 startups as well as working at Nvidia and SpaceX, which are larger companies. And I know that when here in Silicon Valley, I can hire Python programmers. Well, it's hard, but I can do it. There's not enough people out there, but I can hire Python programmers. I can't hire an R programmer. So if I was a startup company and I was trying to create a product, I would not create it in R simply because I couldn't get the right people. My pool of potential developers is tiny. And so there are a few really interesting cases, where people have used Lisp or Scala or other exotic languages to do, websites and things. But largely speaking, right now all the graduates are coming out of the university speaking Python, and I think that leads a momentum. Like it or not, sorry, C programmers, Python has won, and everybody now is working with Python, building tools with Python, and the sophistication of Python is growing very rapidly. There's people with Python compilers. As we look at putting Python onto the GPU and controlling the GPU with Python, we obviously compile the Python to GPU assembly language because we can't run a Python interpreter on the GPU. It's not well suited for that. And so, the challenge for CUDA in Python is, how do I take a language that only thinks about one thread and run it on a machine that has 250,000 threads?
And how do you deal with race conditions there? How do you deal with like the threads sorting and giving it back to the one thread of the language itself? That's the other thing. Like getting your head around that as a developer that comes from a world like that is a totally different story. I mean, the same with like JavaScript with the synchronous and the wait and these kind of things that came out, and people are just like, no, it's not like one thing. The chip is not yours. It could be anything in the machine that you're actually executing on. So I mean, you said like it's hard for you to in the Silicon Valley. I mean, there is this company called WeAreDevelopers, and they have this job board where you can hire people in Europe, and some of them are really good. They speak English too, and they could work like 8 hours before you. So by the time you come to the office, they could have done the things that you needed them to do. Would that be something that you're interested in?
I'm sorry, it just glitched. Could you repeat the question?
Okay, yeah, there's your answer, I guess. Like, yeah, it's tricky to. I mean, I've been remote working for Microsoft for 8 years, and it's a 9-hour difference, and it really is a change for you. But it feels to me like the computing. When we talk about general computing, I think the connectivity, and we are currently suffering bad connectivity in this call, is still a thing. So we say like people can work from wherever, whenever, and it really works out. But I find that there's more and more we have to look into the physical infrastructure that we have right now, and which brings us back to products like CUDA to use everything that you have, because AI is super hungry. Like that's one thing. Did you with the explosion of like Gen AI being a thing? Did you get lots of requests to actually ramp up CUDA to do different things to it, or were you already on the precipice of like we can do all we can, or is there more you can tune to get it to do even more for the end user out there?
The list of things that I want to do in CUDA is enormous. There's always way more stuff that we can think of and that other people come and ask us for all the time. And as I was saying, the AI world has similarities with the supercomputing world that we started in, and so a lot of the infrastructure still exists. But there's also a huge, the emphasis is different, and everything is, everything being in Python changes the way your tools and your tunings and everything work as well. So there's just so many, there are so many things that I wish we could do. One of the interesting challenges that we have is, well, both a superpower and a challenge, is we make the hardware that the language runs on. And that's really lucky in some ways. If I'm Intel, I make the hardware, but it has to suit everybody else's code. If I'm Microsoft, I make the software, but it has to run on hardware that they don't own. And at Nvidia, I get both sides of it. And in fact, in my normal job, even though my job is formally I steer CUDA, but half of my time is spent working with the hardware engineers, because the hardware lifetime, it takes what, 2, 3, 4 years to build a new chip. So we've just released this Blackwell chip, and I am working on the chip after the chip after that chip. Okay. And so you have to look into the future, and who can predict these things? AI changes every 6 months. So it's very, very difficult to know what to build. What people are asking for today will take years to appear if it requires changes in the hardware. Fortunately, most things can be done in software, and so we're constantly evolving the software. But new technologies like strange reduced precisions, other things like that AI has, those things which require hardware support, it takes a few years to come out. So we have to look ahead and predict in some way, look in a crystal ball for what we're going to build. And it's a gamble every time. It's really interesting just to see what things we build succeed and what things that we build don't. The chip does twice as many things as anybody ever knows, because half of the things just turn out to be useless. But there's billions of transistors in a chip at this point, so we can be a bit flexible.
Being the open source person that I am, and open person about technology, I'm very excited that like Python is the language that made it. I mean, when you said like you do the language and you do the hardware, Apple has that with Swift, but Swift is not as taken on, and in terms of like generating things, people build like in iOS apps in JavaScript and compile them rather than just like going completely into that environment. So it's great that the market of developers out there chooses what they want to choose, and it's our job as like hardware and software and framework providers to cater to them to a degree. It was interesting to see the change right now. Sorry, you was you were.
Well, I mean, I was just thinking, in terms of things like what the hardware manufacturers build and what the software people build and what the users then go and use. It's this very interesting symbiotic relationship, right? Where to some extent, you know, nobody comes around and asks, can a GPU please go and do AI? But they went and used it. There's a gaming card, which then went and did physics, which then got co-opted by Alex Krasevsky to go and do AI. And the way that people use these are things we don't expect. But then they use them because we built these other tools in different ways. And so it's this very strange dance that happens, and it always has from the very beginning of computing, between the people building the tool and the ways that different people use that tool. And so it's a very organic way that things evolve, and it takes me by surprise always that I've learned that I'm terrible at predicting where things are going to be, because it'll take a turn 90 degrees to the right all of a sudden, and the things that I thought was a small detail becomes really important. It's very interesting winding road as you build these things.
Yeah, it's interesting to see that like I got tired of gaming really early on because it was always like, okay, that game is not fast enough. Your graphics card is not fast enough for that one. You need a better one. And I didn't want to buy hardware all the time just to play a game. I mean, I'm talking like really old things when people came up with Counter-Strike and my machine was too slow to win against a 12-year-old. So it basically, I just didn't. And then the game, it was this extra world of gamers that were caring about updating their hardware all the time. Me as a web developer, I'm like, I was fine for 5 years until the next version came out. And then out of a sudden, AI came about. And I'm not a big fan of running everything in the cloud or putting my data somewhere else. I'm actually happy to run models on my own machine. And this is where it gets interesting again, where you have to think about like up beefing your machines or getting things into the hardware itself. So with the rise of deep search and actually them having a completely different deep seek, not deep search, having a different approach on the rack, like asking the system itself and using a lot less computing power, it feels like we're in a different world again right now, like where we think the demand for GPUs was much higher, or do you think it's still the same?
I think if you look at the progress of AI, it's quadrupling in sort of capability to performance every year. And I think what DeepSeek did, which is, and it's amazing what they've done. There's some, like, if you look at some of their technical paper and some of the optimizations they applied, it's just incredible. They've done stuff like training their AI to operate in a load balanced way so that their hardware utilization is better. It's just incredible. Like, who thinks of these things? I'm blown away by how brilliant these people are. They have made another factor 4 step that it happens year on year, and they've advanced it basically at the beginning of the year. My experience of computing, though, is that, like my hard drive, when my hard drive gets bigger, I don't have lots of space. Somehow everything manages to fill up my hard drive again. And so I think if you say to people, here is an AI that is now 4 times cheaper, they will the next thing they do is make a 4 times bigger AI instead of just run 1/4 of what they were running before. You know, and to do justice to the DeepSeek guys, they built based on, I think they started with a Llama model, didn't they? And then they built a lot of extra new interesting technologies to it. The technology moves incredibly fast in AI. And so I love it. There's all this scope for completely new new things and new inventions. And some of those things will increase the compute power that is needed, and some of them will optimize the compute power that is needed. And somehow we're at a point where, probably half the people I work with use AI coding assistants at this point. We are already at a point where you can materially have a better, easier day by using these tools. They're already that good, and they're getting better. So, where the state of the art is moves around. But my experience with computing is usually when you optimize and more power rather than saying, okay, great, now I can stop. I, on to that element, to something that you said, where you said, you don't want to work everything in the cloud, you want to work things locally. I think that's something that DeepSeek has shown people, which I think is really good, which is that they can take a big model and they can refine it, they call it, to different sizes, so it can run on a desktop, on a laptop, on a phone. And I think that's the kind of thing that we'll see more, where one of these models, which is trained on a large system, can then be optimized down to something that will run on a smaller system. But there's room to pick how big of a system you want with and get a more or less sophisticated answer. And it's that spectrum will mean that more people can use it, and you don't have to always be operating out of the cloud. But as intelligence increases, I think people will just use more and more compute power as it becomes available.
And I mean, it's like as developers, we're a small bit of that. Like when you think about video generation, when you think about image generation, there's a lot more computing power going on there. There's probably less sophistication in it, but it's actually more a turning of numbers, because if you create a 4K video with like embedded other videos, there's a lot of stuff happening there, and that actually takes a lot of space. Now, we talked about upgrading computers and doing these things, and there's a classic thing called the Moore's law about this, which always said like, okay, here's some limits that we keep reaching and we keep moving. And now a lot of people have announced that that Moore's law is not applicable any longer. So can you refresh us what Moore's law meant, and do you think we are past these limitations that it pointed out as?
Moore's law was the observation back in the 70s that the number of transistors that you can fit onto a chip is doubling every 18 months, 2 years, something like that. And so for 50 years, it's been the case that we can keep packing more transistors onto a chip, which means you can get more performance out of the same size chip. And it comes from shrinking the logic, the transistors on the chip itself. And people have declared the end of Moore's law several times over the course of this prediction. And what usually happens is that the properties of one of these devices changes. And so right now, for example, while we can keep on doubling the chip density, and if you look at the curve of chip density, we are still adding twice as many transistors every couple of years. The challenge we have right now is that the power curve, the power is not halving on every transistor, right? So if my laptop, for example, that I'm using right now to talk to you, has 150 watt battery in it approximately. And so if I double the number of transistors but don't halve the power, I can't turn all my transistors on. So the challenge that we have with Moore's law right now is not that I can't get more technology into a chip and more compute power. It's that physically powering it and turning these things on is not scaling as efficiently as the transistors. And so either you see the chips move into the cloud where you've got higher power devices, or you have to come up with new algorithms and revolutionary ways of doing the same thing for less power. It turns into a story of power, not performance, or if you like, performance per watt. And so for me, that changes everything about how I think about what we built, because it means that you have to have exotic algorithms running on exotic hardware to optimize this performance. One of the things that the Nvidia GPU has is these things called tensor cores, which are very high density matrix multiplication units. They exist because it's more efficient to optimize a dedicated processor block than it is to write generic programs that run through standard transistors. The same is true for texture mapping and geometry management and graphics. It's very natural for a graphics chip to have specialized hardware like this. What I see in the future is more and more specialized hardware, because you need to overcome the fact that the power curve is not keeping up with the transistor density curve. And ultimately, it's going to be interesting to see where that goes. I did a quick calculation just when I was doing an internal talk at Nvidia. If you look it up, it turns out the sun is emitting 64 megawatts per square meter, and an Nvidia GPU emits approximately 1 megawatt per square meter. And so if I keep doubling my density of transistors, then in 6 doublings, which gets me to 64, my chip is now as hot as the sun. And I can't obviously cool the sun. It is a bit glib because the power curve is not quite like that. But largely speaking, if I keep doubling the logic without halving the power, there's no way I can cool the sun. There's a limit to how many transistors I can fit in something. And the only answer at that point is to start scaling outwards, having racks of chips, data centers of chips, because I can't power this thing, I can't cool this thing. I need megawatts coming into the wall in one of these things. It's a weird future for computing, when I need megawatts to be able to keep improving my power like that. And so I think for me, the future that I have to look at for CUDA is given it's inevitably going to be multi-node, multi-chip, data center scale, networked devices, what does that mean to how people program these things compared to where it is today? And that's probably the thing that both keeps me up at night and gets me up on a Monday morning with excitement that I've still got interesting problems to face. Is this transition from I've got everything on a single chip that I'm controlling 250,000 threads on one chip, moving to a future where I'm controlling 2.5 million threads or 25 million threads on 10,000 chips. And that's going to be a change to how you program these chips, how you build these chips, and how does CUDA present a machine like that in a way that can be reasoned about by Python programmers and C++ programmers.
It's interesting. I mean, is it I don't know, like, is it a matter of like physics as well? Is it like we need different materials, new materials that actually don't get as hot with that many transistors? I mean, I remember like back in the days, like overclocked machines with like, I remember 350 megahertz PCs were just water cooled or were just like oil cooled and these kind of things. Are we at the end of physics of like material that we need? Is it the material that we don't know yet that might help with that, or is it just like, yeah, this is how physics work?
I mean, we are up against physics, and that's really what Moore's law and all that technology is about. Is managing to shrink devices and still, how do you make 7 billion devices at nanometer scale and have them all work? It's amazing to me. It fascinates me how they build these things. But quantum physics says that the location of electron is uncertain, right? And so when you have wires on a chip, the electron might just teleport into the wire next door, and your 0 becomes a 1. And you're constantly fighting that in these chip designs. So yes, things like quantum leakage current, things like the amount of power that semiconductors take to fill all of the unit cells of silicon. Effectively, we will need to move at some point to a material that is not silicon. But in the same way, you remember, organic LEDs came along, and everyone said these are the displays of the future, and it took 2 decades really for them to really appear, because LCD screens were not sitting still. They were advancing all the time. Anything that is going to compete with silicon has to catch up with silicon and then exceed it. This is why photonic chips, which would be lower power, are still on the way there, because normal chips are still doubling every 2 years. And your brain, I think I read some of your brain is 1 million times more efficient than a silicon chip per bit. And so there's a huge scope for reducing the power for these things, but it's going to take exotic technologies and R&D. And so, I'll be an old man by the time that kind of thing comes true. I'm fascinated to see where it goes, because when you're up against physics, you can't beat physics. You have to find things that work better in the same under the same laws of physics.
I mean, Star Trek Voyager showed that like biochips is the way to go, but then you can get diseases. That was the bigger problem with that. Like, it's fascinating though. Like, I've seen like the sci-fi of the 70s, 80s, and 90s has inspired so many things. And it's interesting to see that we're actually still have that in our head. Like, we still think of computer help me with something is like the coolest way to actually interact with a computer, and you're like, it's the most inefficient way to a degree, because there's a lot of misunderstanding opportunity. And ubiquitous computing is now more or less what we have. I don't even know a place without wireless anymore. Okay, in Germany I do, but like in general, it's like we kids grow up in an AI world right now. They don't even know what it is, and basically the way we don't care about where the water comes out of the faucet when we open it, they don't even know what offline means to a degree, and what the scaling of that one is. Now, you talked about that we think in the quantum world. So I'm a complete novice at quantum computing, and I remember Google releasing that massive chip where they said, like, it's going to be the solution for everything. Where does quantum computing come into that race?
It's fascinating. I was talking with a friend of mine at Qualcomm about different styles of computing. We've been in a world, I would say, of von Neumann computing for the last 50 years, right? Or more. John von Neumann, who really defined the way that this logic-based, deterministic, state machine style computing that we live in today is working. What we're seeing right now is this shift to what my Qualcomm friend called neural computing, which I love that term, where a neural network algorithm is fascinating because it's not consistent. It produces different results for the same input. It is error prone. It is error tolerant. It can absolutely accept having not every number be the same every time. It's good at completely different things. Problems that are NP hard, that are difficult to solve in a reasonable amount of time in von Neumann computing, can be solved almost immediately in neural computing. It's fascinating to me. It's opened up a whole realm of things that were never possible before. And quantum computing, I think, is another step of another form of computing that is good at yet different things. And I think we're never going to be in a world where one form just takes over everything. The things that quantum is good at is different from the things that neural is good at, which is different from the things that von Neumann is good at. You don't want an approximate answer to your financial spreadsheet doing your taxes, right? You're going to want a real good computing, like good repeatable computing for that. On the other hand, a quantum machine will be solving a million problems at once, right? That's the superposition of quantum states. Not all algorithms fit that, but the algorithm encryption is the classic one that we talk about, that the machine can just look at a problem and solve it, decrypt it, because it can solve every possible problem at the same time. But what the future that I see is one where you've got multiple of these different styles solving a big problem using the right tool for the different jobs. So that a real application of the future, a real sophisticated, complex, AI coding assistant, for example, or something like that. It's not just an AI algorithm. There's also a classical computing algorithm, and in the future there will be quantum computing algorithms, which will, for example, optimize your program by solving every possible pathway of the program at the same time. And so I see a very hybrid, a heterogeneous world where something is made up of lots of different parts rather than one thing dominating.
Cool. I mean, quantum computing needs supercooling at the moment to work, right? So that's like
Yeah,
double electricity being needed. Like,
that is true, because quantum error is a real problem in quantum computing. I think what happens once as they get the stability better in quantum computing, I think that you'll see, in the same way we did for superconducting, new materials and new mechanisms can raise that temperature. Superconducting never made it to room temperature. Maybe it will in the future, who knows? Maybe a quantum computer will solve that problem. Quantum computing right now, you keep it as cold as you can to keep the error rate low. But one of the big areas of research in quantum computing is error correction, right? How do I take this very unstable machine, use lots of different qubits and elect the right result between them, and things like that? It's fascinatingly different problems in quantum computing. But yeah, I don't know if you'll ever have a quantum chip in your laptop. That's probably asking a lot. But your laptop, already most of what your laptop does is through connecting to the internet, and so you'll connect to the cloud and use someone's quantum machine in some appropriately cooled data center, I guess.
Cool. Well, thank you so much. This was incredibly insightful. We haven't talked too much about CUDA, but we showed you all the opportunities that are out there and all the different environments that we will have to deal with. And CUDA is kind of the translation layer that you could work on. So what I was asking your colleague as well, like what I was excited about, like how open is CUDA? Can you contribute to it? Can you as you said, like as a user, you found much more use cases than as the creator itself. How are the feedback channels? How is the contribution back? Can I send code in? Are there pull requests, or is this something that you will do as soon as I convince you to do that?
So, as I said earlier, CUDA is this platform of many layers. The lowest layer is like a device driver, right? Your printed device driver does not take upstream contributions because it doesn't mean anything to do so. Right? If it doesn't, CUDA's job is to control the Nvidia GPU, and so we couldn't take a pull request for something which didn't work with the GPU because that's not the point of the low level drivers. On the other hand, 95% of all the code in CUDA is higher level library code. The majority of it is open source. You know, we have massive scale projects like if you were talking to my colleague Andy, you probably talked about things like Rapids, which is a Python data science platform. We contribute enormous amounts of code up to frameworks like PyTorch, TensorFlow, things like that. All of that code, the GPU enabling code, all of that is open source. Most of our libraries are open source. And so all of those things take contributions. Even low-level software for controlling tensor cores, something called Cutlass, takes pull requests weekly, all the time, adding features, tweaking the way things work. At the very low level, it still controls an NVIDIA GPU. And so some of that low-level device driver stuff is just a function of what the hardware is. But I would say 95% of what sits above that is either open or very, very welcome to having contributions submitted or requested from it.
Excellent. Well, that's your cue out there. Thank you so much for being here, Stephen Jones. I mean, this is great. Like, I learned a lot. I know that there's a lot of stuff to be solved. And I mean, we can now tell people that it's safe to turn on and off your quantum computers because you never know which state they're in. But thank you so much. Any last words for our audience? Anything else you want us to contribute to? Anything you want to advertise?
So the one thing that's coming up that's always really interesting in the GPU world is NVIDIA's GPU Technology Conference, GTC, which is coming up in March. And this year we have a whole program of CUDA material specifically from beginner to advanced level for training and introducing and learning all about CUDA. And all of it is available streaming free online after the conference is done. So please go and check it out, learn what things are up to. We're opening up the Python world to GPU computing this year. There's a lot of exciting stuff going on. So please come and experiment, come and hack on it.
Thank you very much.
Thank
See you
you.
soon.
Bye-bye.